Hello everyone, welcome to another chemistry time with Professor O.A. Ekpete. Today we will be considering high performance liquid chromatography with the acronym HPLC. The acronym HPLC stands for High Performance Liquid Chromatography or High Pressure Liquid Chromatography. Chromatography is a separation technique. Chromatogram is the chromatography result, and chromatograph is the chromatography apparatus. HPLC is a technique for analyzing, identifying, and quantifying each component in a mixture. It uses high pressure to push the molecules through the column packed with the stationary phase. It can find the relative amounts of a component in a mixture. Hplc separates chemicals dispersed in a liquid sample, allowing for quantitative and qualitative examination of which components are present in the sample and how much of each component is present. Don't forget to like, subscribe, and share this video with your friends. Why HPLC? Compared to other chromatographic techniques such as TLC, HPLC is extremely quick and efficient. It uses a pump rather than gravity to force a liquid solvent through a solid absorbent material with different chemical components separating out as they move at different speeds. The process can be completed in roughly 10 to 30 minutes, and it delivers high resolution. It is accurate and highly reproducible. The stationary phase can be silica gel, alumina, cellulose, with small particle sizes, large surface area to make for high resolution, and it is usually packed in a column. While the mobile phase can be non-polar or polar depending on the type of column and materials needed to be separated. The figure 1 on this slide represents the schematic representation of a HPLC system. 1 is the solvent, 2 the gradient valve, 3 the high pressure pump, 4 sample injection loop, 5 analytical column, 6 detector, and 7 the computer. The solvent is used to elute the sample through the column. It can also be a mixture of solvents. Water, very polar, can be mixed with ethane nitrate, less polar, in a ratio of 70 to 30. Single or several samples can be run in succession by loading in the autosampler without any human interference. In HPLC, valves are crucial for controlling and directing the flow of the mobile phase, enabling precise sample introduction and maintaining system integrity. The pump forces a liquid mobile phase through at a specific flow rate millimeters per minute. The injector serves to introduce the liquid sample into the flow stream of the mobile phase. The column is the most central and important component of a HPLC. The column stationary phase separates the sample of interest using various chemical and physical parameters. The sample travels through a column packed with a stationary phase, where different components in the sample interact differently with the stationary phase. A detector measures the compound as they leave the column, providing a signal that is translated into a chromatogram. The computer not only controls all the modules of the HPLC system, but it takes the signal from the detector and uses it to determine the retention time, the sample component, and quantitative analysis. Types of HPLC pumps. There are different types of HPLC pumps. Selecting the best pump for a given separation depends on your application needs and the analyte complexity. There are 7 types of pumps for an HPLC system. We have the isocratic pump, which uses a single pump block and a single solvent inlet line. We have the binary pump, uses 2 pump blocks and 2 solvent inlet lines, enabling high pressure mixing of 2 individual solvents. We'll have the quaternary pump. It uses a single pump block and 4 solvent inlet lines to mix up to 4 different solvents. We'll have the dual gradient pump. Contains 2 independent ternary solvent inlet lines or channels, permitting separation simultaneously. The dual gradient pumps drive increased sample throughput, higher productivity, and switching between applications without replumbing. We have the reciprocating pumps. These use piston to push the mobile phase through the system. We have the syringe pumps. These use a motorized syringe to deliver the mobile phase. And then we have the pneumatic pumps. These use gas to pressure the mobile phase. Hplc pump continues. Hplc pump is also known as a solvent delivery system. It ensures that the mobile phase is accurately pushed through the column. Normal Hplc pumps can handle pressures up to 400 bar. Ultra high performance liquid chromatography pumps can reach much higher pressure up to 1200 bar or more. We'll have different types of pump heads. We'll have the serial heads, which helps in improved flow stability, increased accuracy, and enhanced reliability. And then we'll have the parallel heads, which shows better retention time, improved peak heads, better resolution, and reliability. Elution. The process of the analyte being carried through the chromatographic column by the mobile phase and emerging from the column is called elution. Hplc pumps primarily operate in 2 modes of elution, the isocratic and the gradient mode. The isocratic mode, that is the mobile phase composition, remains constant throughout the analysis, and it is recommended for the analysis of 1 or 2 analytes. We'll have the gradient mode, on the other hand, which uses a varying mobile phase composition, often achieved by mixing different solvent gradient elution, refers to a technique where the mobile phase composition is varied during the separation process to improve resolution and analysis time. We'll have the low pressure gradient, and then we'll have the high pressure gradient. For the low pressure gradient, we use quaternary pumps, while the high pressure gradient, we use the binary pump, which produces high productivity and better separation. Elution is a crucial process in Hplc, enabling the separation and detection of the analyte based on the interaction with the stationary and mobile phase. Choosing the right chromatographic column for high-performance liquid chromatography is crucial for achieving successful separation of your analyte. You will have to consider some properties, the analyte properties to consider, the chemical nature, which we are going to look at the polarity, the hydrophobicity, and charge of your analyte. These will influence their interaction with the stationary phase. We'll consider the molecular size and shape. Larger or irregular shaped molecules require a wider pore size in the stationary phase. We'll also consider the concentration and expected peaks. You consider the amount of your analyte and their peak height. Narrower columns provide better resolution for closely eluting peaks. And then the column specifications are also important. Length and diameter. Longer columns provide better resolution but take longer time for analysis. Shorter columns are faster but offer less resolution. And then we have the particle size. Smaller particles provide higher resolution but require higher pressure. And then the pore size. Larger pore sizes accommodate larger molecules but may result in lower resolution. And then the other thing we're also going to consider is the pH. pH stability. We choose a column compatible with the pH range of your mobile phase. Types of Hplc columns. We'll have several types, but let us look at the normal phase Hplc. Know that the Hplc columns are made of stainless steel to help withstand pressure, and the flow rate is always about 1 to 3 ml per minute. For the normal phase PLC, the stationary phase is polar. You can use silica gel or inorganic particles. And then the mobile phase we will use is non-polar, maybe hexane or other organic solvents. We know that the polar molecules will interact more with the stationary phase and are retained longer, and the non-polar molecule will move with the mobile phase. It is used for the separation of lipids, fatty acids, and other non-volatile compounds. As we are shown in this figure here, we can see that the most polar one was highly retained, the color orange, and then the least polar one, that is the color green, was trying to elute first from the column. The reverse phase Hplc. We have a mixture there. Then we have the compounds, the least hydrophobic, we have the medium hydrophobic, and then the most hydrophobic, all in the column. Which one will elute first? We are saying that for reverse phase Hplc, the least hydrophobic, which is the polar compound, will elute first. The sugars, the amino acid, the salts, the organic acids. And then the medium hydrophobic, like the aromatic compounds, some drugs, the aliphatic compounds, will also elute. And then the most hydrophobic will elute last, as it interacts with the color, e.g. fats and oil and the alkanes, etc. Because the stationary phase is non-polar, meaning they don't have a charge. Mobile phase is polar. Commonly used is water, methanol, and acetonitrile. The non-polar compounds in the mixture will stick longer in the column, while the polar molecules will elute first. It is used for the separation of pharmaceuticals, clinical chemistry, food and beverage, and for environmental analysis. Please hit the subscription button now. Subscribe, because subscription is free. Introduce this channel. Share the videos with your friends, with your children, and your loved ones. We have also size exclusion Hplc column. This stationary phase use are porous beads, particles, often silica or polymer-based materials. We have the mobile phase are aqueous buffers. Common buffers include phosphate, buttered, buffered saline, organic modifier, acetonitrile, tetrahydrophenone, and others. The mechanism is that larger molecules are eluted first, while smaller molecules enter the pores and take longer time to elute. Separation occurs based on the molecular size and shape. It's used for the analysis of proteins, polysaccharides, and polymers, etc. Affinity columns. Stationary phase is ligand with high affinity for the target molecule, such as antibody, enzyme, or metal ion. The mobile phase that is used is a liquid solution, typically a buffer that carries the sample mixture through the column, allowing the target molecule to interact with the mobilized ligand on the stationary phase. The mechanism is that the analytes that specifically bind to the ligand are retained on the column, while other compounds are eluted. It's used for purifying biomolecules, proteins, antibodies, and biotechnology. The types of Hplc detectors, we have the UV-vis absorbance detector, we have the refractive index detector, we have the fluorescein detector, we have the electrochemical detectors, we have the conductivity detector, we have mass spectrometry detector. Don't forget to like, comment, share this video with your friends. Know that the selection of an appropriate detector for a Hplc analysis depends on the nature of the analyte, the sensitivity required, the application, the type, and compatibility. Each detector offers specific advantages and limitations. Know that subscription is free. It costs you nothing. Subscribe to my channel, etc. What is retention time? The retention time is the time it takes for a particular compound to pass through the chromatographic column and reach the detection point. The retention time is useful for identification of an analyte, allowing for the identification based on the time it takes that compound to elute from the column. And then it's good for separation. Retention time differences between alanine enable their separation. And then for quantification, retention time is used to determine the amount of an analyte present in a sample. What are the factors that affect retention time? Column properties, column length, internal diameter, and stationary phase. And then the mobile phase composition, flow rate, and pH also affected. Temperature, column temperature affects analyte interaction with the stationary phase. And then also analyte properties, the chemical structure, polarity, and molecular weight. The Hplc chromatogram. On the x-axis, it shows the time it takes for the analyte to pass through the column, while the y-axis shows the signal intensity, often measured in absorbance units or other detector methods. The peaks represent individual analytes and characteristics, such as retention time of peak appearance, as shown on this chromatogram here. We are seeing that xylose eluted before glucose, glucose before maltose, maltose before sucrose, and lactose, respectively. The peak high signal intensity and peak area under the peak is proportional to the analyte concentration. Well, the summary. Hplc is a powerful tool widely used in various industries for the separation, identification, and quantification of complex mixtures. It is widely used because it offers high resolution, better sensitivity, and improved versatility. Thank you for listening to this lecture to this end. Don't forget to comment, like, and share this video with your friends. Subscription is free. It costs you nothing. Share as we meet again in the next lecture. Thank you very much.